Now I'm talking about atom economy, and the concept is relatively simple. It has implications for environmental friendliness of processes, and we'll be talking about that as well. So the idea is that when you have a reaction, you have reactants, and you have a product or products that you want, and all that you do is you take the RFMs, the relative formula masses, from the left-hand side, and you add them all up. So that's your great big sum of the relative formula masses, which is what that big epsilon means. And then you take the RFM of your product. And the product will typically have fewer atoms in it than all of the reactants combined. And so you divide the RFM of the products, or of the product, by the sum of the RFMs of the reactants. And then, in order to get percentages, you times it by 100, and that gives you the atom economy in percent. So let's talk about two examples. The first example is not actually a chemical example, but it illustrates the problem with atom economy, or the benefit of thinking about atom economy quite clearly, I think. Okay, so imagine you are a gold prospector. So that's a beautifully drawn mountain here. And every now and then you come across a nugget of gold, and you see that's you there with your pickaxe, and you're looking at that nugget, and you're taking it out of the mountain, and you're taking it to a jeweler, or somebody who will buy the gold of you. So that's a beautifully drawn house there where the jeweler lives. And the idea is that atom economy means that if you take the nugget by itself, then you have pretty much all of the gold here, and you take it to your jeweler, and it won't cost you very much in terms of transporting that bit of nugget to the jeweler. So the atom economy is pretty high, because almost all of the mass of that nugget will be gold, and therefore you have a very high yield, a very high return when you give that nugget of gold to your jeweler or to the goldsmith, and they purify it and so forth. But what you could also do, which I wouldn't recommend, is you could take a section of the mountain out, and you could put it on a big old lorry, and you could drive it to the jeweler. And in that rock, you probably have that nugget there, and now it costs you a great deal of money to transport all of that soil and earth and mountain parts to the jeweler. And then all you end up with is exactly the same. So the idea of atom economy is, do you transport your stuff first, or do you make the stuff and then transport the product? And in terms of atom economy, it's always beneficial if the product has got quite a low atom economy, to make the product first and then transport it to where you need it. Whereas if the atom economy is very high, it sort of doesn't really matter. So let's say, as an artificial example, you have water, and let's say you have the water in a particular place, and you're making hydrogen from it. Okay, so you're splitting that up into H2 and O2. That means you need two of them. That means you get two of them, and you get one of the oxygens. And here, what you need to do, let's say the hydrogen is the wanted product. Okay, so you've got a relative formula mass of 4, because each hydrogen is 1, and then you've got, so it's 1 plus 1, and you've got that twice, so that's 4, and then the oxygen is 16, and you've got two of them bound together, so that's 32, and then of course the water is 18, and you've got two of them, so that's 36, so that balances in terms of the mass. But let's say you need the hydrogen gas. Let's say you've got a space shuttle, beautifully drawn space shuttle here, and the tanks need the H2 in them. They actually also need the O2, but let's, for argument's sake, just ignore that and say you need the H2 in those tanks. Would it be better to cart around the water and take that to the rocket and then make the hydrogen? Or would it be better to make the hydrogen first, put that in a tank, and then cart that to the rocket? And I think you can see that in this very artificial, unrealistic scenario, it would be beneficial to make the hydrogen and then cart that to the rocket. Why? Because your atom economy is what you want, the RFM of your product divided by everything that goes into it, which is 36. And then you times it by 100, and that gives you your atom economy. So it's 4 divided by 36, which is 1/9, which in percentage terms is 11.1%. So the atom economy there would be really low. So if you couldn't take the water to your rocket, obviously water is quite ubiquitous. That means it's abundant. That means you get it in a lot of places, and you can obviously build a pipeline, and it doesn't cost that much energy. But that's not the point. The point was that in this artificial scenario, we just transport our product over to the rocket. Because it saves on transporting costs. It means that the products that aren't wanted, in this case the oxygen, for example, aren't transported over either. Now there is another scenario which we just need to briefly mention, which is unwanted side reactions. So let's say, and for this I'm just going to go generic. I'm going to go A plus B gives you C plus D. And let's say D is actually a side reaction which you don't want. That means that the side reaction here, producing D, is actually taking away from your atom economy. So the relative formula masses of A and B would be your total investment in terms of atoms, and then your RFM of C, relative formula mass of C, would be your product that you actually want. And so you can then see that side reactions can reduce your atom economy. So if it was the case that A and B only led to the formation of C, brilliant. But if it leads to the formation of a side product, then you might want to avoid that in terms of atom economy. Okay, and that's it.
Please like and subscribe, and let me know of any questions you'd like me to cover in the comments.